Hi, I've been following along with Paul McWhorter's Raspberry Pi lessons, and he's up to number 19 now. But lessons 15 through 18, he was reading analog using the Pi, but you can't do it directly. You got to use ADC0834 digital analog to digital converter and get your uh, readings digitally from the chip. And when he introduced it in lesson 15, he linked us to a library that we could use to do it. And I followed along through the lessons with the potentiometer and the joystick and everything using that library. But I know when I don't know whether I enjoy it, but I like the challenge of reading data sheets on different chips and microcontrollers and see how they work inside and everything. And I thought that, well, I wonder how hard it would be to do this, read this chip without using a library, just to use the data sheet to try to figure out what it's doing and read the library. So I found the data sheet online. So this is the data sheet. It's made by, this chip is made by different companies. I don't think we have a TI one, but they're all the same. I looked and this is one that I'm using. Almost, I checked like 3 data sheets and they're all the same. So I assume that they worked out the same way. But anyhow, this is, they have like single channels, 2 channels. We have the 4 channel, which is 80834. And then they also have, 8 channels. But so we have to sift through the data sheet to make sure we get the information. Some of it is the same for all the chips, and some of it is chips specific. So we did that. So one of the things I was finding out is, I wonder, like I said, let's go down to number 10 first, page 10. So the timing on it. So what, I guess we'll go back to the top for a second. So these chips, it tells you in the very beginning that this is a serial input output analog digital converter. The multiplexer options, that's some of the options that we have. But anyhow, so this is going to be serial input and output. So there's going to have to be timing and clocks and everything like that. So let's go down and we can look at page 10. So this is the timing page for it. And we have, we know that when we wired this up, we have 3 different pins that we're using on the Raspberry Pi. We have a clock pin, which is an output. We have a chip select pin, which is an output for the Pi. And then we had this data pin that we hooked up. And you hook it to 2 different, that from the Raspberry Pi, you hook it to 2 different pins on the ADC0834 chip. And I was wondering why we did that, but reading the data sheet, we're using it for both data in and data out because they're not used at the same time. And if you read the instructions in the data sheet, it says that this is a legitimate way to do this, is to tie those 2 together, and they won't interfere with each other. So like I said, we got this clock cycle. So the first thing I thought, okay, so how fast does this clock have to be running when we're reading this chip? The thing is it doesn't have to run all the time. You just have to run it, and you need to have at least these 21 cycles to complete the whole channel read that you're doing. So let's see, I think I found that on number 6. So on the data sheet here, it says your clock frequency, the minimum is 10 kilohertz and the maximum is 400 kilohertz. So I decided to pick something in the middle. So I just decided to go with 100 kilohertz and read that. So if you need go from that to the length of your clock frequency, we're actually this is 100 kilohertz. So I actually picked 50 kilohertz because you got a high time when you're clocking your clock. You got a high time and then a low time. So the period that you're high and low, I decided to make it one 100,000. So 40.00001. So that gives you a high time and a low time of, but you got twice that. So it ends up being 50 kilohertz. So I thought that was well within it was higher than the 10, but it wasn't too fast for us. So I decided that that's what I wanted to use. So when I was coding it. And then, like I said, we got the timing thing here. So, and then a little bit later on, you got all these. So when we have to tell it how we want to read. There's different ways of reading. I'm pretty sure we want to use what they call this, not the differential, but the single read. But then you have to use it to tell it what pin you want, which input you want, because we got 4 on the thing. So I just got it set up so that you can pick the one you want. And then let's see. And this here is what we are using for the 0834. We're, like I say, we're using single-ended. And like I said, you got to send it first. It's not listed here, but you got to send it a start bit of 1. And then for this single, you're sending the next bit is a 1. And then between the odd and the select, you're choosing which channel. So it's actually binary, but it's they're not listing it as a binary number. But the odd is actually the least significant bit. So if you look at what channel this plus sign is on, which channels use a 0, it's 0 and 2 are the 0. And then the 1 is the 1 and the 3. So that's your odd, which means that if it's odd number, your channel is either 1 or 3, then it's going to be a 1 there. And so we know that if you do use the modulo operator, mod 2 on that, or divide by 2, and asking if you get a remainder, you're going to get a remainder on odd numbers. So that's what I figured that's what we'll have to do to choose that number. And then for the select, like I said, then you have the 0 and the 1 channel are both 0s, and then the higher channels 2 and 3. So the way to do that one would be to select that if it was greater than, if your number is greater than 1, then it was what you wanted. So figure I'll have to use that math to figure out which channel we're on so that we can do it. But that's what we were doing there. And I didn't have to figure all this out. Like I said, I figured it out myself. I mean, how I was going to go about coding it, but they tell you on here the digital interface and how the conversion actually takes place. That chip select line, you have to pull it low first, and then you got a list of 9 instructions of how you go about getting a full read on the thing. So I just followed that. I'm not going to go step by step through that. I got to show you the code and how we're doing it, but you really want to just keep track of what that is. So I got tired of switching back and forth between pages in here, so I grabbed a couple screenshots and just put the 2 things that we needed, the timing diagram and our how we were going to code it down here. I just pasted them together and got it so that we're doing it, so I could figure out what we're doing. Like I said, we have to start our clock, and then we have to then we do the chip select, and then when it goes low, that's what the whole time it doing the read on your thing, that's going to stay low, and then it's going to go high at the end. So we had that, and then we also have, like I said, this is the part that we have to clock in, that this is coming from the Raspberry Pi. We're sending stuff to the 0834 chip. We have to send it which channel we want to read. And then after we get that, this line here is internal to the chip. I think they bring it out, but we don't need to do that we're not hooked up to that channel or that pin at all. But then after we do that, it automatically realizes, after you have a little bit of a settling time, it says here, that you can start checking. As you clock, you can see what your data is coming out of the chip, and you can read it back into the Raspberry Pi. So anyhow, I had a couple false starts and everything, and it took me about maybe an hour and a half, 2 hours to get it coded right. But we can go over the final code that's actually working so that we can see it. Oh yeah, I didn't mention that they actually, I guess this is so that you can use it like on another, you could send this output, instead of sending it to a microcontroller or a computer, you can send it to another chip or something, that serial to parallel chip or something, that you could get your information out of it, because they're sending it first in the most significant bit to the least significant bit, and then they're turning around and sending it back to the least significant bit to the first most significant bit. We didn't need both of those, so I just read the first 8 and put them in the order that we were looking for in our data byte. And then but yeah, I decided to go ahead. I think it was important to go ahead and clock through all these and just not worry about reading the last part. So I ended up having, I think 21 or 22 clock cycles to make sure that we finished the read, and then we at the end we'll send the chip select back up. But like I said, we actually have to make an output for this pin here, but then after we send the data, we got to actually change that to set up as a input pin, and then at the end we're going to make it an output pin again. One thing that I was a little concerned about, when I was wiring this, I said, wow, we're wiring this to 5 volts, and then the pins on the data pins on the Raspberry Pi aren't supposed to be 5 volt tolerant. I was looking at the data sheet. I didn't bring it up this on the video, but it actually can, the pin data coming off the chip can be as high as 4.75 volts. And I thought, well, that's not 5 volts, but that's pretty darn close. I hope it does. But Paul and a lot of places on the web are using this with 5 volts because this chip is not 3.3 volt compatible. There's other chips that can do 3.3 volt, but not this one. So, but I think because you're only using it for such a short read that it probably, doesn't actually get up to it doesn't get up to 5 volts. It's probably got something just internal, and it guess it's just under the limit to what you want to do on that. But it actually says in there that it's good for CMOS, which is the 3.3 volt chip. So I guess the designers know what they're doing, but it does say in the data sheet that your data coming off of this pin can be as high as 4.7 volts. I mean, yeah, 4.75 volts. So anyhow, what I did is at the end of this, it doesn't tell you to do that, but I didn't want to leave this as an input. So at the end, I also changed this back to an output from the chip so that it's not trying to read that data. So it shouldn't be on there. Plus it says here that it goes into a tri-state mode anyhow. So it's probably it wouldn't put any voltage on the line anyhow. But I just thought it was important to get it out of the input, get that pin out of the input state so it didn't get exposed to 5 volts. Anyhow, so let's get to the code, I guess. So again, I'm using VNC to get into the Raspberry Pi, and I'm actually using Visual Studio Code to do this. And so not using whatever Paul's favorite editor is at this moment, but when I learned from Paul that we were using this Visual Studio Code, and I'm used to it and like it, and probably a little stubbornness on my part. I just want to stick with it. So anyhow, so what I decided to do is make a function to do this, but we had to do, I know when you use the library, you use a setup function, and I said, okay, well, we don't need any setup on this. If you turn this into some type of, if you tried to make it a library, that makes, you would have to do that. But anyhow, so this is just basically using it as is. So we're importing Raspberry Pi or the GPIO library. And then because I wanted to keep my typing, I like to keep my typing to a minimum on when I'm doing these. And as long as it's clear to me, I don't really worry about, I want to keep it as short as I can. So one of the things I did is I'm importing from time import sleep, but I'm making it SL. So all I have to do is type SL and then put the time that I want inside of it. Then we have our pins that we're using, our chip select pin, same ones that the library uses. It's 17, 18, and 27 for the data, but it goes to both input and output. So it goes to 2 pins on that chip. Again, here's the frequency I wanted to use, and I just used the F here because, well, frequency, but it's actually the period of the on time and off time. So I just wanted a real short variable there to use. And then we had to use our set mode, and I set up the chip select is always going to be output, and the clock's always going to be an output. So that was the way I did it. And then, like I said, we're doing a lot of bit flipping on this when it's coming in and reading the output going out. So I decided I didn't want to have to type this here 20 times and this here 20 times and the clock probably 40 times. So I I made these little functions so that all I have to do is put, like the clock, and because all these are just taking 0 and 1 as we're as inputs. So this is the clock as we flip the clock, and then we have one where we're doing, this is called bit in, so it's getting the data that we're getting from our GPIO. So we're returning that bit that we're getting in. And then this is bit out. This is coming from the Raspberry Pi. So we're outputting a value to the data IO line. And like I said, this is the input. So we're reading the data. This was writing, this is reading. So we're doing that. So like I said, these are just 3 short functions that the only reason that they're in there is so I don't have to write all these GPIO outputs all those times. All I have to do is BI or BO or clock. So then here's my function. I call it read ADC, and then we're only parameter we're passing to it is the channel number, so that's 0 to 4. And so our data, we have to have a variable, local variable. So we want to have it 0 when we start our read. And then here's where we're doing our, if you notice, I didn't do the chip select out here because, didn't make a function for that because you're only doing it twice. And so we're making our output and we're running our chip select to low, and we'll keep it that way until the end of the read farther down, and then we'll make it high again to end the read. So, and then, like I said, this data IO, it's going to flip between output and input. So it only happens a couple times, so I didn't worry about a function for that. So we start off with it as being an output from the Raspberry Pi. So the chip is actually reading bits off of that. So, and then we come down here, and like I said, we're doing our, I decided to do it this way. The semicolon in Python lets you put multiple things on a single line, so that I did that so it makes it clear. So the first thing we do on the first line of every one of these is we flip the clock. So we're making the clock 0. And then, like I said, this is a start bit, and it always has to be 1. So we're sending a 1, and then we're sleeping for the frequency. And then it goes to this line, and we flip the clock back, and then we sleep again. So when we're sending data to the ADC chip, we're actually the chip is reading it on the rising edge of the clock. So the data has to be there before the clock goes up. So we're changing that data line to be a 1, and then as it goes from 0 to 1, then the ADC chip's going to read it. So it has to be reading it. I didn't mention it, but when we are reading the data back in from it, we're actually have to wait for the data changes on the falling edge of when it goes from 1 to 0. So we'll have to read it after that. So anyhow, so we're clicking through here, just inputting our what we need. Like I said, these two are always going to be the same. It's a start bit of 1, and we want to use single end mode, so it's always going to be 1. But then depending on the channel is what's going to be here. So the first thing it wants is what the odd bit is, which is, actually the least significant bit of that. So if our channel is 1 or 3, then this channel modulo 2 is going to either be it's going to be 1 if it's an odd number. So if it's an even number, if it's 0 or 2 channel, then it's going to be a 0. So that it's going to send that bit in, and then it's going to sleep. And then this is the select bit, and this is the one, if it's 0 or 1, it's going to be a 0, but if it's 2 or 3, it's going to be a 1. So this is where I do a conditional statement. If the channel is greater than 1, then I tried just using that, but I got an error. It says that it's a true false. It's a Boolean. So I had to add this in and change it to an int. So it's a 0 or a 1. I thought a Boolean would work, but it's a true false didn't work in that case. It wouldn't pass, and a true false didn't work for it. So I had to make it an int, which it makes it a 0 or 1 instead. So anyhow, we're doing that. And then remember, I said it had to have a settling half a clock to settle. So we got that. And then, like I said, I just read the first 8 bits, which is 7 is the high bit and 0 is the low bit. So I did an in range 7 to 0. That's why you put a -1, because it's one less than that, because we're decrementing as we go. And then as we do that, then we're just bit shifting this, we're ORing the data. So this means that we're shifting that 1 or 0 that we're getting as an input to that bit. So we're moving over. The first time through, you'll be pushing that bit to the 7th position. Next time you'll be to 6th position, 5th, 4th, all the way down to 0. And you're putting whatever you're reading on that line. And then, like I said, we had those other readings for going the other way that we didn't care about. So this is just going through and clocking the clock, flipping the clock so that we could finish the thing. And then we just, like I say, we just changed the chip select to 1. And then I also wanted to make the data pin an output again, just so it wasn't exposing the Raspberry Pi to any higher voltage any longer than it had to. And then we're just returning whatever the data is. So like I said, this is creating a 8-bit binary number, but it's 0 to 255, so that's good. So that's my function. And then I decided to, I just don't test this out. I just got it wired up with a single potentiometer on channel 0. So I just decided to read it once a second. Remember, my sleep is SL, so once a second I'm doing that. And then we're doing Control C to clean up the output. Let me get myself out of the way here and we can run this. Let me see, I got change my potentiometer down here. So moving my potentiometer. And it goes all the way to 0. So it sure seems like it's doing what it's supposed to, and didn't have to use a library. So that's kind of fun. Anyhow, I'm going to cut the video here. On lesson 19, Paul was talking about using how to use a servo. So I figure I'm going to keep this function that I got, and he wanted to use a potentiometer to control a servo. That's on Arduino. That would be the sweep sketch, which you can do in about 10 lines of code. So it's a little harder with a Raspberry Pi. So we're going to find out how that works. But so anyhow, just wanted to show you that you don't always need a library. If you can read the data sheet and figure out what it's doing, you can make your own functions and do it. Anyhow, thanks for watching and look forward to more of Paul's videos.